Welcome back. We will start with session 14 on differential cryptanalysis. We have two talks. The first one is extending the quasi-differential framework from fixed key to expected differential probability. It's a paper by Christina Boura, Patrick Derbez, and Baptiste Germont, and Baptiste will give the talk.
Okay, so thanks for the introduction. So the quasi-differential framework is a framework that was originally designed to study the validity of differential distinguishers. And the fact that this is the first theoretically sound framework that studies the fixed key probabilities of differential distinguisher motivated us to propose, so in this work, two theoretical extensions and their application. Okay, so first I will recall some bases on differential cryptanalysis and then we will move on to our contribution. Okay, so this is a technique that was introduced in 1990, in which you study the propagation of an initial difference through a cipher. And the goal for cryptanalysts is to find a couple of input and output differences such that the input differences propagates with a certain probability to the output difference, and we want this probability to be greater than the same probability, but for a random permutation. Okay, and in order to evaluate this probability, we people usually rely on the fact that so this is computationally intensive to evaluate this probability. So instead, we use the fact that most ciphers are iterated ciphers. So this means that we can fix the intermediate differences after each round. And now we do not have to, we can only study the propagation of differences through one round instead of the whole cipher. And so we call the tuple of intermediate differences a characteristic. And we want the same distinguishing property for the characteristics, the same condition on these probabilities and for differential. Okay. But in fact, this is a little bit more complicated because when an attacker wants to mount a concrete attack on a specific implementation of a cipher, then the key is fixed. So we are rather interested in the fixed key probability of a characteristic. And so we want to find a characteristic such that the fixed key probability of the characteristic verifies the distinguishing property for any given key. But the problem here is that estimating the fixed key probability of a characteristic is a really hard problem. And so people have used several assumptions for decades. The main one being the stochastic equivalence hypothesis. So basically, it says that you can so it means that the fixed key probability of a characteristic can be approximated by the average over of all fixed key probabilities over all the keys. And this average is called expected differential probability. And you assume another hypothesis, which is the round independence. So this means that you can compute the EDP of your characteristic as the product of the one round probabilities for each one differentials that compose the characteristic. Okay, so this is the assumption that people usually do to estimate the probability of differential characteristics. But in fact, we know that they do not hold in practice since like the beginning of differential cryptanalysis. So already in 1992, Knudsen observed a deviation of the fixed key probability on the characteristic that was used to attack the death. So what I mean by deviation here is the fact that the fixed key probability significantly varies depending on the key that you use. There have been also some other results on the AES characteristics, such as the fact that they are most of them are plateau characteristic. So this means that for some keys, the probability of the characteristic is equal to 0. So you cannot mount any attack on those keys. And for some others, all the valid keys share the same probability P. So you can represent your probability distribution as a plateau function. And another work that is of great interest is a work from Pera and Tan in 2022, in which they developed an heuristical approach to detect key constraints. And they analyzed a lot of characteristics on Skinny and other ciphers, but mainly on Skinny. And they were able to show that only one out of a lot of characteristics was valid for more than 50% of the keys. So this means that a lot of attacks published on Skinny or even other ciphers may be invalid due to those assumptions. And a milestone in this topic is work from Tim Bine and Vincent Reimann, in where they developed the quasi-differential framework, and they are able for the first, so they provide a theory of quasi-differential, and they are able to give an exact formula for some characteristic. They're able to give exact formula for the fixed key probability of characteristic. And this is done in a systematic way, so without relying on any heuristic. Okay, so before moving on our contribution, I will just explain what this framework is about. So in classical differential cryptanalysis, you study the propagation of differences after each operation of the cipher. And for each transition from one difference to another, you compute a probability coefficient. And then you use the assumptions that we made to compute the overall probability of your characteristic. Here, in this framework, you add another dimension, which are called masks, so the UI on the figure. And you compute you study the transition of a pair mask difference to another. So let's say you look at U1A1 to U2A2. And for each transition, you compute what the correlation coefficient, which is given by this formula. So what we are looking at is the probability that a linear approximation holds for the valid pairs that follow the characteristic. Okay. And so as you can propagate those pair of mask difference to each operation of the cipher, you have a notion of trail. And if you want to compute the correlation of the whole trail, you can just do the product of each correlation coefficient, and it gives you the correlation of your trail. Okay, but now you may wonder where the key is in all these things. So if you consider a key addition, you have the following correlation coefficient that appears, and you can see that in the green term, there is some key material that is implied. So this means that the correlation of quasi-differential trail will depend on bits of the key. So you overall, yeah, it depends on bits of the key. And this is really important with this theorem that states that the fixed key probability of a characteristic is given by the sum of correlation over all the quasi-differential trails that share the same intermediate differences at your characteristic. So basically, you are given a characteristic, so the AI, you value over the mask, you find a lot of quasi-differential trail, you compute the correlation of each of them, then you sum them up, and you obtain an exact formula for the fixed key probability of your characteristic. And here, we do not make any assumption. So this is why this framework is really promising. And yet, there remain some open problems regarding its use and its practicality. So in this work, we address mainly two problems. The first one is the extension to the related key setting. So we found that studying related key characteristic in this framework we have another problem when if you want to compute the exact formula for one differential characteristic, it means that you need to exhaust all the clusters of quasi-differential trail associated to this characteristic. And it can be really hard to do or even infeasible in some cases. So it gets even worse when you need to analyze thousands or hundreds or thousands of them, which can be the case when you look at clusters. So what we propose is to, instead of computing the fixed key probabilities, we compute the EDP. So we tweak the original framework that was designed to study fixed key into a framework that can study average probability. And it takes into account the key schedule. So this means that we can compute the average fixed key probabilities over all the keys generated by the key schedule. And this is the first time that we have such results on the key schedule. Okay. So now I will just explain those two extensions. So the first one. Control framework is the following. So you study you introduce the transition matrix TF, and then you look at TF tensor itself. And on this matrix, you apply a change of basis to obtain what is called the quasi-differential transition matrix, so DF here. And the fact that we look at TF tensor itself means that we apply the same function f on both elements of the pair. And this is a problem with the related key setting, because on the key addition, you add one key k to one element of the pair, and a key k plus a certain difference on the other element. So you do not have a symmetric operation, and it did not fit in the framework. So what we propose is just to replace TF tensor TF by TF tensor TG, and we perform the same change of basis operation to obtain a new quasi-differential transition matrix. And we can prove that we can derive similar theorems as in the original framework. And for the case of related key, it does not come without any additional complexity. So if you consider f to be just the key addition of a key k, g k plus certain constant, so a key difference, then you have the following correlation coefficient. And you can see in the red term that the mask after and before and after, so the masks are the same before and after the key addition. So this means that you do not have any additional propagation behavior. And so really the complexity of analyzing related key characteristic is the same as for single key characteristic. Okay, so that's the first extension. So now moving on to the second one. So I recall that we want to analyze clusters of characteristics. This is computationally infeasible or really hard. So what we do is we study, so yeah, for example, if we want to study a truncated differential, then we need to analyze thousands of characteristics. And as I said before, it is not possible. Okay, so what we want now to do is to compute the EDP of characteristics. So if we step back on what the quasi-differential framework does, you give a sequence of operation, and then you are able to compute the probability, fixed key probability, you are able to compute, the probability of a characteristic over all the inputs as a function of the key. What we want to do with EDP is to compute the probability of a characteristic over all the inputs, over the plain text, and over all the keys. So what we propose to do is just to plug in the key into the data, the inputs. So what this means is that we do not look at a function on the plain text only. Two components. So here, the plain text. Then only the correlation on the plain text will vary, will change after the operation. So this means that you can propagate the key schedule and the data path independently until you reach a point where the two components are implied in your function. And this operation is the key addition. So for the key addition, we have the following formula for the correlation coefficient. And I will break down each term. So the first one is just classical difference propagation. So it means that the difference on the input path, on the plain text path, is equal to the sum of the difference on the before the key addition on the data path and on the key path. So this is really classical. Then you have the second term, which says that the mask on the data path remain unchanged. This is the same for the difference on the key. And now we have a new propagation behavior. So the mask on the key path will be equal to the sum on the mask on the key path before and on the data path before. So you just sum them up and you have your new mask. Okay, so now we have described like the behavior of mask propagation for each operation. So we can have this beautiful formula. So don't get scared. It really is the same formula as in the original framework, but the key is in the quasi-differential trail. And now you do not compute the fixed key probability, but the EDP of your characteristic. So that's what we get. And now you may think that adding additional degrees of liberty with the key in your quasi-differential trail will make things even worse as before. So of course, this is on this slide, sorry, the fact that the mask in the input mask and the output mask must be equal to 0. This, combined with the propagation behavior that I described later before, means this is really a lot of constraints on the quasi-differential trail. So we find actually really a few trails that verify that are of such form. And intuitively, it can be explained by the fact that when you do not integrate the key in the quasi-differential trail, then one trail will explain a local effect on some keys. But when you add the key in the trail, then it explains a global effect for all the keys. So this is not surprise that we find less of them than in the original framework. Okay, so that's it for the second extension. So we developed MILP implementation to test our extension. For the AES, we test any new impossibility results, but we are able to confirm that the EDP matches the heuristical estimation that people made while taking the key schedule into account. So this is really important to notice. And we also applied it on Skinny. So on Skinny, we found new results in the fixed key model as the work from Perrin and Tan. So we detected a new constraint on one differential characteristic. And we also applied our EDP computation on those trails. So we were able to obtain more accurate results when also for characteristics that were complex. So it was done experimentally before. And you can see that in parentheses, you have the number of trails that we found. This is really a few trails compared to what we get with the original framework. So just to give you an idea, we would find for the same characteristic like thousands, hundreds of thousands even, trails. So this is really an improvement on this. And we also finally applied it on a truncated differential that was used in a differential meet in the middle attack. So we analyzed this number of characteristics, and we were able to prove in a quite short time that more than half of them are invalid. And for the other part, the probability is actually higher than expected. So we improved overall the attack by a factor 2 to the power almost 3. And yeah, so that's it for this part. So to sum up, we extended the quasi-differential framework to the related key setting. We also provided, for the first time, a formula for the EDP that takes the key schedule into account. And yeah, we developed a practical MILP model. And with it, we obtained some new results on the AES and Skinny. So thanks for your attention.
Thank you. Are there any questions?
Thanks for the talk. So I want to know how many quasi-differential trials have you counted in your experiments? Can you exhaust all of them, or just stop at some numbers?
For the EDP computation?
Yeah.
Okay. So for this, actually, we found so few of them, but the model is so basically we can set a lower bound on the correlation on the absolute correlation of trails that we want to find, and yeah, we need to stop it until a certain level because it becomes quite infeasible. But it doesn't mean that you will find a lot of trail for the lower correlation, but just that the model is like too slow to deduce really. So it cannot detect like impossibilities sufficiently fast. So yeah, it runs forever. But you can set lower bound. Not sure.
But it's still possible that many small, very small probability quasi-differentials can cluster to cancel some.
I think it's quietly yeah, it's
in theory.
It's not probable for me, but that there are so much trails that compense the probability. Yeah.
Oh, okay. So for the AES case, maybe the previous page. Yeah. So how many cases in your experiments that the mask for the key value when added into the state is non-zero.
Sorry, I didn't get the question.
Okay.
How many traces do we find?
Yeah, no choice, because in our experiments we find the mask of the wondering how many cases in your experiments that's non-zero.
I'm not sure to understand the question.
Okay,
Sorry.
okay. It's okay. Thank you.
Thanks.
Other question? Yeah. If not, let's thank the speaker.